46 years ago, Mount St. Helens killed 57 people in the worst volcanic disaster in American history. This week, the same mountain is shaking again. A swarm of small earthquakes has been registering beneath it, paired with a second signal that seems to make no sense, a surface that is sinking instead of rising. It has people watching this volcano the way they watched it in the spring of 1980. In the next few minutes, you will learn what that shaking actually is, and how scientists tell the difference between this and a real countdown. On Thursday morning, a cluster of very small earthquakes registered directly beneath Mount St. Helens, the most dangerous volcano in Washington state. The two networks that watch the mountain around the clock, the United States Geological Survey's Cascades Volcano Observatory and the Pacific Northwest Seismic Network, formerly located only a handful of them. One came in at about magnitude 0.9 near 8:21 in the morning. Another registered near magnitude 0.8 about an hour later. On paper, that is nothing. Quakes that small are not felt, not heard, and not remarkable for a living volcano. But here's the part that stops you. That swarm arrived while the mountain was doing the exact opposite of what your instincts tell you a waking volcano should do. Mount St. Helens is not bulging, it is not swelling. Its surface, measured continuously by instruments bolted to the mountain, has been settling downward for years, sinking. The intuitive picture, the one everybody carries in their head, says earthquakes plus a rising volcano equals magma climbing toward the surface. What St. Helens is actually showing you is earthquakes plus a surface that is quietly sinking, a volcano that is shaking while it settles. Let me be clear about the stakes before anyone panics. As of this weekend, Mount St. Helens sits at volcano alert level normal, aviation color code green. There is no eruption warning, no official body is forecasting one. This is not the mountain about to blow, but it is also not nothing. And the reason it is not nothing is the whole point of what follows. A volcano can be very much alive, actively rebuilding its plumbing miles below the ground, and still stand years or decades from an eruption. The question underneath this swarm is the one that actually matters. And it is more unsettling than any single earthquake. If St. Helens is quietly refilling beneath a sinking surface, how would anyone know when the quiet turns into a real countdown? And are we even watching the right signals? To understand why a tiny swarm matters, you have to follow the plumbing down. Mount St. Helens is not a simple bucket of lava sitting under a cap. It is the top of a system that reaches 16 meters into the crust. Down at that origin, near the base of the crust, magma forms and begins its slow climb upward. It collects in a storage reservoir far below the surface, roughly 2 and 12 to 6 miles beneath sea level. That reservoir is the mountain's engine room, and it is the key to everything. When that underground system takes on new magma, when it recharges, the reservoir presses outward on the rock around it and above it. That pressure forces fluids through cracks. It stresses the crust. And stressed cracking rock does exactly one thing. It produces small earthquakes. This is what scientists call a recharge swarm. The name tells you what it is. It is not the sound of magma breaking for the surface. It is the sound of a reservoir refilling miles down, pushing gently on the rock that pens it in. The earthquakes are a symptom of the mountain feeding, not the mountain erupting. It helps to sit with just how small these earthquakes are. The magnitude scale is not a ruler. It is a set of stairs, and each full step down is a large drop in the energy released. A magnitude 0.9 is not a slightly weaker version of a quake you would feel. It is thousands of times fainter, the kind of event that exists only as a squiggle on a sensitive instrument. You could stand at the exact spot on the mountain, above one of these quakes, and never know what happened. That is the scale we are talking about. Dozens of whispers from a reservoir far below, not a single shout from magma near the top. And it is why the location of the quakes matters so much more than the raw count. A 100 whispers from 2 miles down means something completely different from a single sharp crack a few hundred feet under the crater. That distinction is the difference between a routine week and a genuine emergency. And it hangs entirely on where the quakes are and what the ground above them is doing, which brings us to the strangest number in this whole story. The one the internet has decided means window, most of them too small to be pinned down and added to the official catalog. So which is it? A handful or dozens? The honest answer is both. And understanding why is how you inoculate yourself against the conspiracy version of this story. A claim circulates every time this happens, that the agencies are deliberately hiding earthquakes, that for every couple they announce, dozens are buried. It sounds compelling because the raw traces genuinely do show more wiggles than the catalog lists, but that gap is not suppression. It is physics and arithmetic. For an earthquake to be formally located, the same signal has to be detected at multiple stations and pinned to a point in space within tight error bounds. A microevent too faint to register cleanly at more than one station simply cannot be located. And neither can the constant noise of the mountain, the wind, the ice, the rockfall, the rumble of distant quakes on the other side of the planet force all of that into the catalog, and you would not have better data. You would have garbage. And here is the detail that quietly demolishes the cover-up narrative. The seismic network itself, back during a similar swarm, stated in plain language that there were many more events too small to be located. They said it out loud. The catalog is not a ceiling that hides the truth. It is a floor that openly admits it is a floor. The uncounted quakes are not a secret. They are acknowledged. That transparency is the best rebuttal there is, and it means the located versus visible gap, unsettling as it looks, is not evidence of anything being hidden. It is evidence of a monitoring system being careful. There is a reason the raw trace looks so busy to an untrained eye. A seismograph does not record only earthquakes. It records everything that shakes the ground. And near a mountain, that means wind bending the trees, a river rolling boulders, a truck on a distant road, ice cracking, and the faint ring of large quakes. Half a world away. Somewhere inside that constant hum are the real micro-earthquakes, and the job of the network is to pull the signal out of the noise with enough confidence to put a dot on a map. When an event is too faint to clear that bar, it does not get thrown away in secret. It simply stays below the threshold, visible as a wiggle, but not solid enough to call. The catalog, in other words, is the conservative count on purpose. It would rather miss a real whisper than invent one. If Thursday's swarm feels unprecedented, it is worth knowing that St. Helens did almost exactly this 10 years ago, and nothing happened. In the spring of 2016, starting around the middle of March, the mountain began producing a swarm of small earthquakes. Over roughly 8 weeks, the network formally located more than 130 of them at depths between about 2 and 7 kilometers. And noted again that many more were too small to locate. The magnitudes were tiny, mostly 1/1/2 or less. The largest, only about magnitude 1.3. The rate climbed until the mountain was producing close to 40 located earthquakes a week. That sounds alarming until you look at what came with it, which was nothing. No unusual gas, no swelling of the ground, no shallow earthquakes creeping toward the surface. The United States Geological Survey looked at the 2016 swarm and stated flatly that there were no signs of an imminent eruption. And what they were watching, they explained, was recharge, the magma reservoir slowly refilling exactly as it had done before. And they pointed out that this process can continue for many years beneath a volcano, without producing an eruption at all. It is worth being honest about what happened at the end of that 17-year recharge, because it is not what the word eruption makes you picture. When St. Helens finally did erupt again from 2004 to 2008, it was not a repeat of the catastrophe. It was a slow, grinding extrusion of thick, pasty rock that piled up into a new dome inside the crater. Spine after solid. Spine of it over 4 years, dangerous up close, monitored the entire way at nothing like the sideways blast of the disaster. That is the range of what recharge can build toward, and most of it looks far more like a mountain slowly rebuilding itself than a bomb arming. The refilling is real. The outcome, when it finally comes, is more often a construction project than a detonation. We know that because St. Helens has already shown us the mountain recharged quietly for about 17 years from 1987 to 2004 before its next eruption arrived. 17 years. So when you hear that St. Helens is shaking again, the correct reference point is not a countdown clock. It is a mountain doing the same slow, patient underground thing it has done over and over on a timescale measured in years and decades, not hours and days. But that still leaves the sinking. The one thing 2016 and this week share that nobody can look at without flinching. Here's the paradox stated as plainly as I can put it. The reservoir far below the mountain appears to be refilling, and yet the surface of the mountain is going down, not up. Those two facts feel like they cannot both be true. A refilling tank should bulge. It should push the ground up. Instead, the instruments show years of subsidence, the surface settling toward the ground rather than rising away from it. For a long time, this is exactly the observation that convinced people something was being covered up because it seems to violate common sense. It is not. And the resolution is the single most important idea in this entire story. So, let me walk you through it. The system has 2 levels and they are not locked together. Far below, miles down, the reservoir can be re-ressurizing, taking on new magma, charging like a battery. Scientists have actually documented this at St. Helens after the mountain's last eruption ended in 2008. Monitoring showed the underground magmatic system repressurizing, the reservoir slowly reinflating from about January of 2008 onward, even while the volcano sat silent at the surface. That is the charging half. Now the shallow half. Up near the top, the young lava dome that the mountain built during its last eruption is doing what fresh volcanic rock does. It is cooling, it is crystallizing, it is degassing and contracting and settling under its own weight. During the late stages of that last eruption, a receiver sitting on the active spine measured it sinking about 2 centimeters a day. All of those shallow processes pull the surface down. So you get the strange, true, and completely non-contradictory picture of a volcano charging far below while its shallow skin cools and sags above. The deflation and the recharge are not fighting each other. They are happening at different levels, decoupled at the same time. The surface sinking does not mean the magma is leaving. It means the top is cooling while the bottom quietly fills. This is also why the mountain keeps fooling us. In 2023 and 2024, St. Helens produced the largest short-term jump in earthquake rate since its last eruption ended. And then again, nothing eruptive followed. It all stayed within the range of background noise. And in September of 2025, the Geological Survey had to publicly reassure people the mountain was not erupting after large plumes were seen rising off the peak. Those plumes were 45-year-old ash from the 1980 eruption, lifted off the flanks by strong wind. Not an eruption, a ghost. A mountain so famous for one catastrophe that its own old ash thrown up by a gust can start a panic. To understand why that one catastrophe casts such a long shadow, you have to go back to it. Because 1980 is the yardstick that tells us what today is not. The reason Mount St. Helens carries the word deadliest is not abstract. It earned it on the morning of May 18, 1980, in the worst volcanic disaster in the history of the United States. And the value of going back there now is not to frighten you. It is to show you precisely what a real countdown looks like so you can measure this week against it. Because 1980 was loud and visible and accelerating, in every way, this week is quiet. The reawakening began in March of 1980 after 123 years of dormancy with earthquakes and bursts of steam. Then came the part that has no equal in the modern record. The whole is the textbook precursor that today's mountain is pointedly not showing. What made 1980 a countdown was not any single number. It was the acceleration. For 2 months, the signal stacked and intensified. The earthquakes did not stay faint and far down. They grew and climbed. The steam explosions became frequent. The bulge did not appear overnight. It swelled visibly day after day until it was deforming faster than the rock could hold. Anyone watching the instruments that spring could see the trend bending upward toward the surface, toward failure. That is the texture of a real reawakening. A set of signals all growing, all shallowing, all pointing the same way at once. Hold that image because it is the exact opposite of the flat, faint sinking picture on the mountain this week. Then, at 32 minutes past 8 on the morning of May 18th, a magnitude 5.1 earthquake shook the bulge loose. The entire north flank collapsed at once, the largest landslide ever recorded on Earth. And with the side of the mountain suddenly gone, the pressurized system inside was uncorked. It blasted sideways. The lateral blast tore outward and flattened forest over roughly 230 square miles. It removed the upper 1,300 FT of the mountain. The summit dropped from 9,677 FT to 8,363. Ash reached Idaho by around noon. It rated a 5 on the Volcanic Explosivity Index, and it killed 57 people. One of them was a scientist. David Johnston was a volcanologist with the Geological Survey, monitoring the mountain from an observation post about 6 miles away, a distance everyone believed was safe. When the flank gave way, he had seconds. His final radio transmission, 3 words, became the defining human moment of the disaster. Vancouver, Vancouver, this is it. The observatory that watches the mountain today was built in the aftermath of that morning, and it carries his name. That is the weight 1980 still holds. And it is exactly why the contrast with this week matters so much. Set the two side by side because this is the whole argument. 1980 was a surface bulging outward at 5 FT a day. This week is a surface sinking. 1980 was earthquakes climbing toward the surface as magma forced its way up. This week is tiny earthquakes miles down where a reservoir is quietly refilling. 1980 was accelerating, shallowing, and inflating. 3 signals all pointing the same direction, all screaming upward. This week is faint, far, below, unsettling. Everything about the 1980 signature that made it a countdown is absent from what St. Helens is doing right now. That is not a guarantee about the future. It is a reading of the present, and it is the honest one. The instinct that says something is wrong here is misfiring. Nothing is wrong. Something is simply on the way it has been on off and on for decades. The genuinely sobering part is not this swarm. It is the realization that the mountain's true countdown, when it eventually comes, will look different from the false alarms, and that St. Helens has a long proven habit of standing down again and again until the one time it does not. Which raises a fair question. If this refilling is happening far below, what is actually refilling it? And why does this particular mountain keep coming back to life when its neighbors sit quiet? Music. Mount St. Helens does not refill itself by accident. It sits at the surface end of one of the largest machines on the planet. And to see the machine, you have to go offshore. Just off the coast of the Pacific Northwest, a slab of the seafloor called the Juan de Fuca Plate is being forced beneath the North American continent. This is the Cascadia. Subduction zone, the same fault system capable of producing the magnitude 9 megathrust earthquake that hangs over the entire region. As that slab grinds downward into the hot interior of the planet, water trapped in the rock is squeezed out and driven up into the mantle above. That water lowers the melting point of the mantle, and the mantle begins to melt. The magma it produces rises, and where it breaks the surface, it builds volcanoes. That is the Cascade Range. Rainier, Adams, Hood, Baker, Shasta, and St. Helens. A line of volcanoes standing behind the subduction zone, each one fed by the same offshore engine. And St. Helens is the most active of them all. It has erupted more often and more recently than any of its neighbors, which is exactly why it is the one watched most closely, and why a swarm beneath it makes news while the others sleep. The recharge earthquakes miles below the mountain are simply the near-surface end of that plate scale machine. The magma conveyor, ice, reaching up to touch the world we live on. There's a reason St. Helens, not one of its taller neighbors, is the mountain that keeps making news. The magma it produces is a thick, high silica type called date, and thick magma is dangerous magma. It does not flow easily. It traps gas, builds pressure, and when it fails, it tends to fail explosively rather than pouring out in gentle rivers. St. Helens is also young and unusually active geologically speaking, a mountain that has rebuilt and torn itself apart many times over. That combination, a busy volcano fed by sticky, gas-charged magma, is exactly why a small swarm beneath it draws attention. That an identical swarm under a quieter peak never would. The stakes are simply higher here. If you have followed this channel, you have seen the other end of the same system in action. The magnitude 5.6 earthquake off Vancouver Island at Cascadia's northern edge was that plate boundary flexing. The worst-case Cascadia megathrust scenario, the one that threatens the coastline itself, is that same slab locking and eventually letting go. The offshore fault that could level cities and the mountain quietly refilling in the forest are not two separate stories. They are two faces of one machine. And St. Helens is simply where that machine occasionally clears its throat. So if the engine never really stops, the real question is not whether St. Helens will wake up, but how we will recognize it when it finally does. The reassuring news is that scientists are not guessing about what a genuine reawakening would look like. They know the tells because the mountain has shown them before, and none of them require a crystal ball. A real countdown would announce itself with a specific set of changes. And they are the signals worth committing to memory because they are the ones that actually matter. The first would be a migration. Earthquakes shifting from far below where recharge lives upward toward the surface, tracing the path of magma on the move. The second would be a change in the character of the shaking itself, the onset of what is called harmonic or volcanic tremor, a continuous vibration that signals fluid and gas moving through the plumbing rather than rock simply cracking. The third would be the reversal of the very thing that makes this week so strange. The surface would stop sinking and start to rise. Measurable inflation would replace the deflation trend. The ground swelling as pressure finally reaches the shallow system. The fourth would be a rise in volcanic gas pouring out of the mountain, carbon dioxide and sulfur dioxide climbing as magma nears the top. And the fifth would be steam explosions, the mountain clearing its throat with bursts of superheated water exactly as it did in the weeks before 1980. None of that. Not one item on that list is happening at Mount St. Helens right now. What is happening is a faint patient swarm far below a settling surface, the signature of a volcano refilling on a schedule measured in decades. The countdown signals are the absence at the center of this story, and their absence is the reason the alert level has not moved. Just as important, this is one of the most heavily instrumented volcanoes on the planet. St. Helens is wired with seismometers, satellite radar that measures ground movement down to the millimeter, gas sensors, and geodetic receivers, all feeding an observatory built specifically because of what happened here in 1980. That density matters. It means the shift from quiet recharge to genuine reawakening would not sneak past unseen. The signals would show up one after another in instruments designed to catch exactly them. The reason today reads is routine is not that anyone is looking away. It is that the people looking hardest, with the best tools ever pointed at this mountain, see a volcano refilling, not volcano rising. So where does that leave us this weekend? It leaves Mount St. Helens exactly where it has been, alive and refilling and standing at normal with a small swarm that is far more interesting than it is dangerous. The mountain is not counting down, it is doing maintenance. The slow underground work of a volcano between eruptions and the sinking surface that looks so alarming is simply the top cooling while the bottom fills. There are a few concrete things worth tracking in the coming weeks, and they are the same things the observatory will be watching. The first is the swarm itself. Does the rate climb toward the roughly 40 a week pace of the 2016 episode hold at a trickle or fade back into silence? The second is the ground. Does the deflation continue, flatten out, or the one that would genuinely change the story, reverse into inflation? And the third is whether the Cascades Volcano Observatory says anything at all about this activity. And if it does, whether it uses that one telling word, recharge until one of those signals changes. The takeaway is steady, and it is honest. A volcano can shake without swelling, refill without erupting, and stand at normal while its plumbing quietly fills far below. That is not the beginning of the end. It is the sound of a living mountain between chapters. The day the real countdown starts, it will not look like this week. It will look like 1980, loud and shallow and rising. And the whole point of watching now in the quiet is so that when that day comes, nobody mistakes it for one more false alarm. We will be tracking it.